we will start with power dissipation in CMOS inverter. There are three kinds of dissipation in CMOS inverter. We will look at it one by one. Number one, called dynamic power. Then number two is called short circuit power. Okay, and number three, static power. Now, dynamic power dissipation is associated with the charging and discharging of C out that we saw yesterday, right? Dynamic characteristics we saw. So we saw the output capacitor getting charged through PMOS transistor, and then it is getting discharged through NMOS transistor whenever those transistors are turned on. And short circuit power is also something that you have seen when you plotted the current transfer characteristics. Depending upon the voltage at the input, there is a current that goes from the power supply to the ground. So there is a range of voltages where this current can flow, that is during the transition from low state to high state or high state to low state. In between voltages there is a range of voltages where both are turned on condition. So that's only for a short time, when the input pulse is rising or when it is falling. So I can say when both NMOS and PMOS are in on condition. That's only for a short period of time. And the last is basically leakage power through the the transistor in off condition. Okay, so let's see one by one. So first let us look at what is dynamic power. Dynamic power dissipation. So again we are going back to what we were looking at in the last class or yesterday in the lab also. So we have an PMOS which is connected to VDD, and then we have an NMOS connected to ground. Both of their gate are shorted, and that is where we give the input, and input varies as a function of time, and we looked at what happens to C out. Now I am putting C out, all the capacitor associated with the PMOS and NMOS, there are parasitics, and there is CL, all put together. I am included in the C out. So during charging, what happens? Charging, when PMOS is turned on and NMOS is off, so what is going to happen is the capacitor will get charged like this. We saw the waveform. Now we are looking at how much is the power taken from the, or first we will calculate the energy and then we will find out the power. So power is basically energy dissipation per unit time. Okay, so let us calculate the energy. So during the charging process, what is the energy? That is, so it's a question. What is the energy provided by the power supply during the charging of C out? What is the energy supplied by the power supply? So what is the expression for energy? Energy is basically integral of instantaneous power. Okay, so energy is E charging. So this is the energy supplied by the source. So that is basically integral from, let's say that we are charging from starting from 0 time we are charging, and charging goes up to infinity. The voltage given by the power supply is VDD, and the current given, this current I charging, let's call it I charging into dt. Now this current is actually flowing into the C out capacitor. Therefore, capacitor current voltage relationship I can write 0 to infinity VDD into current through a capacitor is basically C out d V naught. This output voltage is V naught of t. So C dV by dt is basically the current flowing through the capacitor, okay, where V naught is the voltage across the capacitor and C is the capacitance. So this into dt. So I substituted for current, the charging current. That's all what I did. Now what I can do is, since there is a dt here and a dt here, I can convert this integral in terms of voltage. So at infinity the voltage become VDD. So if I integrate with respect to voltage, then I should, at time t equal to 0, we are assuming V naught is 0. So we are looking at waveform going like this during charging. Okay. So this is basically, ideally at infinity only it reaches VDD. It starts from 0 and goes to VDD. We have seen this waveform yesterday. So VDD is basically a constant in the integral. You can take it out. C out is also a constant. So those things we can bring it outside. So VDD, C out, they are constants, and then we have d V naught of t. So this is equal to VDD. So if you integrate this, you will get VDD. Lower limit is 0. So we can write it as C out into VDD squared. So this much is the energy supplied by the source for charging the capacitor at the output. Okay, now but that doesn't mean that all this power got dissipated. So now we will ask a different, slightly different question. How much is the power stored in the capacitor? So this is question number 1. Question number 2. Out of this power supplied by the source, power supply, how much is getting stored in the capacitor? So what is the power stored, or energy I should say, what is the energy stored in the capacitor. Okay, probably you have learned the formula of energy stored in a capacitor in your earlier classes, maybe plus 2 or something like that, but let's basically find out that. So energy stored is what? That's also an integral, 0 to infinity. The instantaneous power, that is basically V naught of t, that is the voltage across the capacitor multiplied by the current, into C out d V naught of t by dt into dt. Okay. So only difference is that earlier when you calculate the powers or the energy provided by the source, we take the voltage as VDD, but now we are looking at energy getting stored in the capacitor, so we have to take the voltage across the capacitor, not the voltage provided by the source. Okay, so this, if you evaluate, again C out is a constant, integral 0 to VDD. We convert the time integral to voltage integral, and here we have V naught and dV naught is what we need. So integral of V naught is V naught square by 2. Put the limit, so we will have half C out VDD square. So that's exactly half of the power that is supplied. So half of the power that is supplied by the source is getting stored in the capacitor, which means that the remaining power is dissipated in the resistor. And the resistor here is the CMOS on resistance, RP. So therefore what we can understand from this consideration during charging is that out of the energy C out VDD square supplied by the source, half of it is stored in the output capacitor, that is C out, and the remaining half gets dissipated in RP. I hope you understand what is RP. Yesterday we did problem to find out RP, etc. So RP is the on resistance of the PMOS. Now let's look at the discharging condition. So to look at discharging, the path is like this. So this is basically a capacitor. We will assume that it was fully charged to VDD voltage. So let me draw that. So this is our C out. So C out. We used to start with at V out at t is equal to 0. This was VDD. We will take this initial condition, and then it gets, so this is our Rn, it gets discharged through this. So the switch will get closed at t equal to 0. So that is NMOS getting turned on, the capacitor begins to discharge. Now all the power that was stored in the capacitor C out will get dissipated in Rn. So So the energy, so here what is happening is the energy stored in the capacitor is fully dissipated in Rn, which is the on resistance of the NMOS, during the discharging process. Okay, so the total dynamic power dissipation is basically the sum of the power that is dissipated. So so let's first add up the energy. Total energy dissipated in one cycle. One cycle means one charging and one discharging. It is charging plus discharge is equal to what? Let's call it as ET dynamic is basically half C out VDD square was the power dissipated during charging, and the same amount of power was stored, so that also get dissipated. So therefore the total dissipation is basically C out VDD squared. So that's the energy dissipated per cycle. Therefore P dynamic is equal to how often we are charging and discharging. Suppose if we charge and discharge F number of time, F is the frequency, that is the number of cycles per seconds. So then you can write it as ET dynamic into F. So where F is the number of cycles per second. So power is basically energy dissipation per second. So this is per cycle, so multiply it with the number of cycles per second, so that will give you, so this is equal to, so we have C out VDD square into F. Now what is the value of this F? So that depends upon the clock frequency first of all, the value of F depends on the clock frequency. If you operate the device at a higher clock frequency, then F is going to be larger, and something called activity factor alpha. So what is activity factor? So a particular node where you apply the input to a device may not change during every clock cycle. There may not be any charging and discharging in every clock cycle. Some of the time it may be just staying at the same value. So it depends upon what is the activity factor. Alpha is basically a parameter which tells you how often we change the input. Every clock instance we may not be changing input. Okay, so if every clock cycle we are changing the input, activity factor is basically 1. That means there will be a charging and discharging in every clock cycle, and therefore activity factor is 1. But usually that is not the case. If you consider a combinational circuit, there may be many inputs and there may be many outputs, and in between, if you look at any gate input, there may not be changes at the input of every gate during every clock cycle. That's not necessary. So the value of alpha, where alpha is basically less than 1. Okay, so therefore P dynamic can be written as alpha C out EDD square F clock. Okay, so that's about P dynamic. Now let's go to the short circuit power. So that's the second dissipation. Now we will look at second is short circuit. So before we look at this evaluation of the second power dissipation factor, so number 2, so this is something that we have seen in the transfer characteristics, but let me show you in a different way. So this is yesterday's circuit. Only thing is that I have put the capacitor, output capacitor to 0. I can remove it. So let me remove the output capacitor. Okay, so this is our yesterday's circuit. Same model parameters, etc. Okay, hope you can see this. And now I am giving a pulse waveform. Look at the way I have specified the pulse waveform. Though the parameters for this NMOS and PMOS is such that the rise time and fall time is somewhere around 100 picoseconds. That means 0.1 nanosecond. But now I am giving a pulse waveform with input rise time is 10 nanosecond, which is much slower compared to the rise time and fall time of the inverter. Inverter had 100 picosecond was our rise time fall time value that we around roughly. Our propagation delay also was something like that, 0.1 nanosecond. But here the input is varying at a very slow rate. It takes 10 nanosecond, that is like 100 times slower than the speed of the inverter with which we can operate. So I am raising the voltage from 0 to 5 volt in 10 nanosecond, and also from 5 volt to 0 volt in 10 nanosecond, and I am giving a period of 100 nanosecond and plotting it for 300 nanosecond. So let us run this. So let's see the input. As you can see, the x-axis it's at a much slower rate. Okay, it takes 10 nanosecond to rise to 5 volt, 10 nanosecond from 5 volt to 0 volt. So this is the input that I am giving, and now what I am going to plot is basically the current that is flowing into the drain terminal of the NMOS. Okay, so this is how I can see the current. Okay, to make it more clear, let me just plot for only 2 cycles. So that means I'll plot till say 200. Input, so there is a 2 cycle current flowing into the NMOS transistor. Okay, so input is varying very slow rate, and if you closely observe this current waveform, our focus is on this current. So this is basically the short circuit current that you are seeing in the blue color. Now when does the current starts to flow? The current will start to flow when the input is rising and when it reaches 1 volt. Okay, that is the time when the NMOS is getting turned on. Until that time, no current. Okay, so let me take the cursor. Okay, so I'm going to place the cursor at the location where the current is starting, and then another cursor at the point where current is stopping. Okay, so this is like the 2 ends of the triangle that you see. Okay, current is starting. So you can see, if you look at here, I have put it roughly, and if you look at here, cursor 1. Okay, so this is showing with respect to the current. So current is microampere. It's now 7 microampere. So roughly I can make it 0. Okay, so now it is 1 microampere. So that's the time when, and if you look at that cursor intersecting the input waveform, it is getting intersected at a vertical point which is corresponding to 1 volt. Okay, so to see that, we have to bring in the cursor for this. So the point where current is starting, or so that corresponds to a voltage basically equal to 1 volt. Okay, and similarly, if you take another cursor and put it on the other end of the place where current goes to 0, you will get it as 4 volt. Okay, so you can see roughly 4 volt. So 1 volt and 4 volt. So from 1 volt to 4 volt, in between those 2 points, the current rises and falls back to 0. Okay, so that is what basically the short circuit current. So now if I plot that short circuit current, first of all, let me draw the input waveform. Slowly I am rising, and then it stays at high state, and then slowly I am Now the critical point is when NMOS getting turned on. So that is corresponding to a voltage VTN. So this is V in, and high voltage is or VDD, and then before VDD I have another critical point. This is basically VDD plus VTP. Okay. Now let me plot the current. So from this point the current starts, goes to a peak value, and same thing happens with falling edge also. Similar triangle here also. Okay. Now if we have same rise time and fall time, so the rise time and fall time for the input T rise, this is for input, not for the inverter. Inverter it will be much lesser. Here we are operating at a much slower rate. In order to just take out this effect clearly. So this is also for the input. So the current will reach some peak value, which we call as, so that's the time that current is going to be determined by a condition where both are maximally on. Okay, both NMOS and PMOS are maximally on, so it is like a short circuit from VDD to ground. So there is a path. Usually in CMOS that path doesn't exist. That is true if the input is either at 0 volt or 5 volt, any of the digital states. But during the transition that is not true. So we are looking at a slow transition so that we can clearly see this short circuit current. So this current we will call it as peak of the short circuit current. Okay. So this is what in an earlier experiment I asked you to find out. You can do that from the static characteristics, because you are basically slewing or gradually varying the DC input voltage in the DC analysis, and then you will be able to see the corresponding current also. Let's assume that this period for which the current flows is equal to T. It need not be same for rise and fall, but let's assume that this also is to simplify the analysis. So let's assume that this is also T. Otherwise we have to take it as T1 and T2 and do it. But let's assume that the input variation, rise time and fall time, if it is same, then T1 and T2 will be same. Okay, so just to distinguish, I can put T1 and T2. So if T rise is equal to T fall, so for the input, okay, V of T, then T1 is equal to T2 equal to T. Now What is the power dissipation? So to find out this power, again this power is supplied by the source, and this is our current, short circuit current. So short circuit energy is equal to integral VDD, that is the power supply voltage which is giving out this current. It is flowing from the power supply to the ground, into I short circuit dt. And to find out for one cycle, we need to integrate for one cycle. So there will be one rise of the input voltage and one fall of the input voltage. So now this integral VDD is a constant, so I can take it outside. Now what is this current? Integral of the current is basically area under this, right? So there are two. So this is that is integral of the short circuit current dt. So that is equal to VDD, area of the triangle. So if you are considering both rising of the input voltage and falling of the input voltage, then so let us write both. This is given by half, area of a triangle is basically half base into height, which is IP, T1 into IP divided by 2, and similarly half T2 IP. So under the assumption T1 equal to T2 equal to T, so if T1 equal to T2 equal to T, then E short circuit is basically VDD. So these two terms become same, so we can write it as IP VDD IP into T. Okay. Now, what is this T? So we should come up with an expression for T so that we can write it more appropriately. So where T is basically you can connect it with VTN and VDD plus VTP. So the total voltage change is basically VDD. So what I will do is I will take the slope, find the slope of this. So the slope of this input variation, so the slope which I showed there is basically T rise or VDD divided by T rise. It's the same as VDD divided by T fall if they are taken to be equal. And another way I can write is this is equal to VDD minus VTN plus VT. Okay, so VDD minus VTN, so I have subtracted this portion, then I have from here to end, but if I add VTP, which is negative, so that portion will also be cut off, and this divided by T. So this I can use for finding T. So what is T? So T is equal to VDD by T rise sorry, I have to invert this. So I will take T to this side. So I will write it as VDD minus VTN plus VTP. Keep in mind that VTP is a negative quantity. So this divided by VDD into T rise. Okay. So I am assuming T rise is equal to T4, just to simplify the analysis. Otherwise you have to take separately these things. Okay, so therefore now I can substitute this T in this equation. Therefore E short circuit energy dissipated is VDD into IP into VDD minus VTN plus VTP divided by VDD into T rise. I can put T fall also because they are treated equal. So this will get cancelled. So I have the final expression IP, or let me write the voltage first, VDD minus VTN plus VTP into IP T rise. Okay, so this is per one cycle, the energy dissipated in one cycle. Therefore power short circuit is going to be equal to, like before, alpha into energy VDD minus VT plus VTP into IP into T rise into F clock. Okay, so both of this dynamic and short circuit power depends upon the clock frequency and the activity factor. So therefore we can call this as the transient power dissipation. Okay, because these are happening during the changing of output states. Is equal to P dynamic plus P short circuit, which is, so alpha is common to both, then you have VDD minus VTN, or let's write dynamic first. Dynamic was C out VDD square plus VDD minus VTN plus VTP into IP into T rise into F clock. So that is the total transient power that is dissipated. Okay, now comes the third one. What was it? It was basically the static power. That is basically the leakage power. So for completeness we can discuss this also. Static power. So this power is dissipated continuously, whether the input or output is changing or not. It doesn't depend on that. Even when the input is at one particular state. So to find out this power, we have to go to the current transfer characteristics, which we have already done in static analysis. Okay. So if you remember graph, so this is the triangle which just now we saw. But if you magnify and see, the current does not really go to zero. I'm just showing that part. Okay, so this is basically V in, and V in varies from 0 to VDD. That is how you do the DC analysis. The current, so this is our IP and all. Okay, the short circuit current be considered from here to here. It starts when it is VTN and then it goes up to VDD plus VTP. This we have already considered. What is between? Now I am looking at a point which is prior to VTN. So there is a current actually which is so negligible, which flows even when the input is at low state, correspondingly the output is at high state, which means that your NMOS is off here. So NMOS off and PMOS on in this region. And similarly we have this region where our NMOS is on and PMOS is off. In both of this region we have a non-zero current. This current is very, very small, and nevertheless it is not a zero. This is basically the leakage current that we looked at in an earlier class when we studied the short channel effect. So this is also called as the quiescent current. Okay, IDDQ. Okay, when the input is at a steady state, then there is a current that is flowing due to the leakage through the transistor, which is in off condition. So that may be like very, very small current. Maybe it's like femto ampere or something like that. So therefore, because of this current, so here also there is roughly they are equal. and they are very, very small. Now what is the power? If this current is IDDQ, then the P static I can write P static is basically VDD into IDDQ. Okay, and this is power, not energy, because voltage into current is basically energy. So we are assuming that either the input is at low state or high state, and under that condition there is a small current which is flowing. Multiply that with the power supply. But this becomes significant if your device is, or for example your mobile phone, you switched it on but you are not doing anything, you are not working out any application, so it's just staying on. So the transistors inside your mobile phone chip, it will be either in low state or high state. So as you keep it like that, what is going to happen? You need the static energy is going to be integral of P static dt. So if you do keep it for large duration, though this power is small, but if you keep it on for a large duration, it can drain your battery. So that is why usually there is a automatic sleep mode most of the computers and mobile phones are having. So that is whenever you are not using the system, the power dissipation should be minimized. So it should go into what is called as a sleep mode. Okay, so the reason behind that is to reduce the time for which the IDDQ is flowing. So it will just stop the IDDQ and save the energy in the battery. Okay, so this is the expression for static power, dynamic power and short circuit power. Okay, so we'll stop here.